Hello, everyone, and welcome to today's EHS Daily Advisor webcast brought to you by Anguil and Verantis. My name is Michelle, and I'll be serving as your EHS Daily Advisor moderator for today's program, entitled Air Pollution Abatement Technology Overview. Ensure ongoing compliance with MACT, NSPS, NESHAP, and state VOC and HAP regulations. Today's program is 60 minutes. Before we get started, I just want to take a few minutes to quickly introduce to you our speakers for today's event. Here with us today, we have Brian Kunkle, Director of System Sales at Verantis Environmental Solutions, and Scott Bayon, Director of Sales at Anguil Environmental Solutions. Thank you both for joining us today. I also wanted to introduce Mary Resnack, Corporate Marketing Director at Verantis Corporation, who will be going over some of the features on today's console for you. Thank you, everyone, for being here today. Mary, the floor is yours.
Thank you, Michelle. Our webinar platform is completely interactive, and what that means is basically all of the windows that you see in front of you can be resized, minimized, maximized, moved around. So basically, fix it however you want for whatever your screen size is. A recorded version of this webinar is going to be available later on demand, and all the interactivity that I'm going to show you is going to remain as well. If you should happen to lose your sound, there's a red widget, an icon at the bottom. That's basically where the sound is. So take a look there first, make sure that you didn't accidentally mute yourself. But if you continue to have issues, hit the little question mark icon, or in the Q&A section, let us know that you're having problems. As in reference to the Q&A, on the left-hand side of your screen, that is where you actually submit your questions. To keep ourselves on track, we're going to hold basically all of the questions until the end of the presentation, but you can submit them at any time. If we don't get to your question live at the end, don't worry about it. We'll contact you later, make sure that you get an answer. As you can also see on the left-hand side is the resource list. This is available for viewing and printing at all times, and that's right now and also later on if you want to come back. One of the items you might find particularly interesting is the summary sheet. And in particular, if you're taking the quiz at the end for the professional development hours, this is something that would be probably pretty useful to you. We also have slides of the presentation that you can print out. And we also have some literature both for Anguil and for Verantis. If any of you need additional PDH hours, just to let you know, there's a URL there for Verantis EDU. We have 2 additional webinars for the rest of this year that you can get hours and credits. And we also have 4 that are available on demand, so feel free to go over there and register for any of those. Finally, if you take a look on the bottom, all the widgets that you see, I'm not going to go over every one of them, but if you hover over them, it'll tell you what the functionality is. 2 widgets in particular that are important for the PDH portion are the test and tracker widget, and they are marked here. So if you look, at the end, you will need to take the quiz, which is the green widget, and right next to it is the tracker widget, the yellow one, and that'll basically show you if you are fulfilling your requirements. Once you have fulfilled all the requirements for the credits, you can actually print your certificate with that yellow widget. Just to talk again a little bit more about the webinar and the PDH portion of it. The webinar value is 1 professional development hour. You must be present for at least 50 minutes to get credit for it. This is both for on-demand or if you come back, both live and also if you come back on-demand later. If for any reason you get interrupted, you can come back to the later on-demand version and finish this out. You must complete and pass the test, which is doing 8 out of 10. When you're done with all the requirements, you can print certificate out. Again, go to that yellow widget. And you can also come back and print it out later if for whatever reason you lose it. You need to keep a record log. This is for your own purposes. A lot of your state websites will actually have different types of spreadsheets that you can keep track of these things. But I suggest that whatever programs you do, you keep track of it in that format. Verantis is going to keep these on hand for about 6 years, so if at any point you do need to get some verification, you can come back to us. And then finally, any problems that you have with the PDH portion of this, please contact me directly. And we are going to move on to Scott here.
Thanks, Mary. Again, my name is Scott Bayon, Director of Sales with Anguil Environmental Systems, and I'll be talking for roughly the next 20 slides or so. And I'll be covering the thermal and catalytic oxidizer portion of the presentation. And then when I conclude, I'll hand it over to Brian Kunkle, and he'll handle the wet scrubber side of it. After that, we'll have the Q&A section and then the quiz at the very end. So some of the topics that will be covered throughout, which applicable industries are we talking about here, so you'll have an idea of where these technologies are applied. Some of the airflow concentrations and ranges, we'll talk in terms of volumes, and then solvent or VOC concentrations that explain to you, which technologies can be applied to the various ranges there. The different options in terms of the equipment, so there's a handful of different oxidizer, both thermal and catalytic, that we'll talk about, how we go about selecting those. Unique airstreams, and this is where we'll kind of tie the whole presentation together, how oxidizers and wet scrubbers are tied together towards the end of that, and that's how we'll transition into the wet scrubber side of it. Different removal efficiencies, that's another one of the key factors that will determine which of the technologies we look at for any given application. And then the last bullet point there, operating costs. That may be the #1 factor for a lot of you that will determine which of these technologies that we'll select. Now, before we get too far into it, we do have our first poll question for you. So what we'd like to know is, have you ever been involved in the selection of a thermal oxidizer and or wet scrubber system? So we're going to give you 15 or 20 seconds or so. So if you could pick one of those options there, and then we'll move on to the next slide, and it'll show the results. Okay, so about half of the audience here has not, and then the rest a little bit of a mix of one or the other or both. Okay, well that helps us gauge, I guess, the experience here in terms of what we're looking at. This slide, so now we're getting into the actual technical slides here on the oxidizer portion. So this slide covers all the technologies that I'll be talking about. And essentially, this covers all the oxidizer technologies that are out there. There are subsets of each of these that you could have individually mentioned, but for the most part, this covers them all, and I'll touch on each one of them. The majority of my time, though, will be spent on the technology in the upper left-hand corner, the regenerative thermal oxidizer, or the RTO, as it's referred to. The reason I'll spend the majority of my time talking about that is that is by far the #1 technology right now in terms of oxidizers. I would say 75% of the oxidizers that Anguil sells are RTOs of some variant. The next one over, still on the top, the thermal recuperative oxidizer, operates in terms of the oxidation process the same as the RTO. The difference there is the means in which we achieve the thermal efficiency and the heat recovery, so there will be a slide on that. The next one over, the catalytic recuperative oxidizer. This is the one that differs a little bit from the thermal oxidizers in that the oxidation process, the actual chemical reaction, is the same. We just use a catalyst to lower the temperature, whereas in thermal oxidizers, we're dependent just on the temperature alone to achieve the oxidation process. The one in the bottom right-hand corner, and then the one in the bottom middle, which is our direct-fired thermal oxidizer, and then our enclosed flare/vapor combustor. I'll kind of talk about these two as if they're the same technology. They're a little bit different, but for the purposes of this presentation, they're very similar. And they're also the opposite of the RTO in terms of thermal efficiency, where the RTO is designed for relatively larger air volumes and fairly dilute air streams. So what we're trying to do is achieve very high thermal efficiency, again, to reduce operating costs. The DFTO, or the enclosed flare, have no internal heat recovery. So they tend to be used on very low air volume and very rich hydrocarbon or solvent streams. And then the last technology that we have there in the bottom left-hand corner, the emission concentrator. It's not necessarily a new technology, but we're learning where to apply it more and more here to different applications. So I'll talk at the very end of my section here about that, kind of how it works and what industries you can apply that to. So before we actually get into the nuts and bolts of the various technologies, I like to put this slide in here just so we're all on the same page of what oxidation actually is. So this it's a chemical reaction. Keep that in mind. And the definition is you have your hydrocarbon or your solvent or your VOC combined with oxygen. And in many cases, oxygen is present. If we're treating an airstream, the oxygen is already present. We add in heat, and the result is the hydrocarbon or the VOCs are broke down into CO2, water vapor, and more heat. Now this applies to all of those thermal oxidizer technologies I had just mentioned. The equation is the same for the catalytic unit as well. The only difference is there's a catalyst present just to lower that operating temperature. And the other reason I like to put this in here is it's important to note that oxidation is an exothermic reaction. So that more heat, in some of these cases there is a lot of heat generated just through the oxidation process. And the amount of heat that's generated, and many times dictates which of the technologies we'll lean to. Now, to get the destruction efficiencies that we're looking for, and in many cases we're 98%, 99%, some applications even greater than that, we need to achieve what is referred to as the 3 T's, which is the first T is time. That's the residence time within the combustion chamber that will actually hold the process air. The temperature is the combustion chamber temperature. Typically it's 1,500 degrees Fahrenheit or so. So we'll hold the process air for a certain amount of time, and that time is typically half a second or so at the second T temperature for 1,500 degrees Fahrenheit. And then we need turbulence. We don't want laminar flow, so we do need to have proper turbulence to make sure we get mixing. And if the oxidizer is designed and operated properly, those 3 T's will result in, again, 98 to 99% destruction efficiency. So what are we targeting here? VOCs, volatile organic compounds, HAPs, hazardous air pollutants, and HAPs are essentially VOCs with just additional harmful side effects. NOx, nitrous oxide emissions, and then the last one on there, odor. People tend to not realize you can use oxidizers, specifically thermal oxidizers, for odor control. So this is the start of the RTO portion of it. And across the top, you see the broad range of applications. You know, we list 5 there. The only reason we listed 5, we could have covered the page with the applications. Again, this is by far the #1 technology when it comes to oxidizers. The airflow ranges that we're looking at 1,000 CFM on the small side up to 80,000 CFM for a single unit. The determining factor there on the large side is just shippability. Once they get larger than that, it's difficult to ship them. So what we would do is if you have a system that's larger than that, we would essentially build 2 smaller systems, operate them in parallel. On the lower end, the reason that it's really not applied to streams lower than 1,000 CFM is it becomes cost prohibitive in terms of capital costs. Some of the other technologies that I'll talk about on those lower ranges are more applicable. The concentration range, 0 to 25% LEL, which is the lower explosive limit of the specific compounds we're dealing with. That also tends to coincide with what the NFPA allows you to treat without other additional safeties in place. Energy efficiency, 95 to 97%, and this is really what it gets down to in terms of why the RTO is the #1 technology right now, is we can achieve 95% on the low end and 97% on the high end of thermal efficiency. And then on the destruction efficiency side, when the RTO technology was first introduced, and this is 30 plus years ago, this is not a new technology, it's been around for a while. But there were some shortcomings on the destruction efficiency side where, you know, low 90s, maybe 95% is what we could get. Now we're routinely getting 99% on a standard RTO, which is really what we're talking about in this presentation. There's a different type of design out there, a multi-chamber RTO, where we can get up to 99.7% overall VOC destruction efficiency. So the schematic in the upper left-hand corner kind of talks about, in a very general way, how an RTO operates. So if you can follow along, starting with the process exhaust fan and the blue colors and the white arrows, imagine that fan is the inlet. That's where you would tie your process into. And that fan is designed to overcome the pressure drop through the RTO, which is roughly 20 inches of water column. So your process will discharge into that fan. The fan will then push the air into a set of diverter valves. And here we're showing 2 poppet valves, one on the bottom that's in the blue stream and then one on top that's in the red stream. So following the arrows, and the blue is indicating relatively cool temperatures, where the red you can see we're shifting from the cool to the hot. So as the fan discharges into the first set of diverter valves, that valve controls the direction of the airflow. And in this case, we're showing a clockwise direction. So we're going up through the left-hand chamber of the energy recovery chamber full of the ceramic media that I'll talk about in a second. And as the relatively cool air travels up through the ceramic media, it's preheated. So we have preheated air then coming into the actual combustion chamber, which is the horizontal portion at the top where you see the actual flame. That's where the oxidation occurs. So now we have clean hot air because, again, this is an exothermic reaction, going down now through that second bed of ceramic, which mechanically is the same as the inlet bed. So now we have hot air going down through the second bed of ceramic for a time period of about 3 minutes. So we're preheating that outlet bed. The ceramic is now stripping all of the heat out of the hot air, and it's maintaining it in that ceramic bed. The air then discharges into the second poppet valve, and the clean air goes out the exhaust stack. Then what happens is every 3 minutes, those valves will switch directions. So now instead of going in a clockwise direction, the same process occurs but in a counterclockwise direction. So that outlet bed that has all of this heat stored in it is now our inlet bed. And the inlet bed is now our outlet bed. So that's really the nuts and bolts of how the RTO works. We're taking all of this energy, storing it in one bed, and then flip-flopping it to the other and putting the air in the opposite direction. And again, that changes about every 3 minutes. Now, to put some temperatures to this whole screen here, assuming, easy math, assuming we have 10,000 CFM of air at 100 degrees Fahrenheit coming into the system fan, we will enter the bottom of the inlet bed of ceramic at the same 100 degrees. As it travels up through that bed of ceramic, by the time it comes out of roughly a 5-foot deep bed of this ceramic, we've preheated it to 1,400 degrees Fahrenheit. We need to operate at 1,500 degrees Fahrenheit, so all we need is enough energy to heat that air 100 degrees. And that's where it gets into the whole reduced fuel consumption and ultimate lower operating costs of the RTO. So this is the one slide I have on the ceramic itself. Really, it can be broken down into 2 main types. The first type you see in the upper picture there is random packing, often referred to as saddles. You can see by the shape there that they kind of look like a saddle. The other type is structured media. Now, there are probably 40 different variations of each one of these. The key thing to remember here is if the RTO is designed properly and the media is chosen properly, these will all do the same thing in that they will all be able to achieve 95% on the low end thermal efficiency. Now the key here is with some of the newer structured medias, we can actually achieve even higher 97% thermal efficiency. Some of the additional RTO options that we have out there, a hot side bypass. Now, a few slides back, I had mentioned we can get up to 25% LEL within an RTO. To achieve that, we would need a hot side bypass, and essentially what that does is divert some of the hot air around the outlet bed of the RTO, essentially derating the thermal efficiency of the unit and allowing us to process higher VOC loads. Bake-out feature, the best way to think of a bake-out feature is like a giant self-cleaning oven. If you get some buildup of organic particulates within the ceramic itself, we have this built-in feature that will, essentially what we'll do is offline get the temperature within the beds to 600 degrees or hotter in some instances degrees Fahrenheit. It'll volatilize any of the organics built up, turn to ash, and essentially just blow out this stack. Again, similar to how a self-cleaning oven works. The supplemental fuel injection, or SFI, If we do need additional energy input, the schematic I showed a burner. That's a pretty standard way to get the additional energy we need. A second way of doing that is we can actually shut the burner off completely and inject the natural gas into the process airstream. And really what that does is artificially increase the percent LEL of the process stream using methane as the solvent or the VOC. Puff or purge capture chambers. Essentially what these do is every time an RTO, the valve switch, there is a very small amount of untreated air that kind of sneaks through the valves and is diverted directly to the exhaust stack and into atmosphere. These puff chambers, what we can do is capture that small amount of air that slips through every time the valve switch and route it back to the inlet of the system. So we capture it and divert it back to the inlet rather than sending it out the exhaust stack. And what that does is it allows us to achieve, rather than say 99% on a standard unit, we can get up to 99.3. It's also used for odor applications where if you have a very pungent compound, what you don't want to have is every 3 minutes a small amount of it going out the exhaust stack. You're looking at potential neighbor complaints. That's where this puff capture system would be used. And then lastly, the induced draft fan. That just means we'll take that system fan, which in the schematic showed it on the inlet pushing through. We'll take the fan and put it on the outlet side of the RTO and pull. Really two instances where we'll look to do this. The one is where it's a highly or a heavy particulate application where we want to keep the fans clean. We'll do that. Or secondly, when I'll talk about these halogenated or applications where we're going to create some inorganic acids, we'll also do that just to make sure the entire system is under a negative pressure and that if there are any leaks, the leaks are into the RTO or into the scrubber rather than out to atmosphere. The next technology, catalytic oxidizers. I just have one slide on each of these next few technologies. We say here, typical ranges are in the 100 to 100,000 CFM range. In reality, they tend to be more applicable to the smaller ranges. I would say the vast majority of catalytic oxidizers are applied to the 100 to probably 5,000 CFM range. The reason being is 5,000 CFM, that's right around the point in terms of size where the RTO is actually cheaper in terms of capital cost and operating cost. So we see very few catalytic units sold bigger than that. In terms of LEL concentration, the same 0 to 25% applies with the same that the RTO can handle. And again, now the catalytic unit operates at a lower temperature due to the catalyst. So we're operating at typically 600 degrees Fahrenheit rather than 1,500 or so degrees Fahrenheit as the RTO. So you may think it's more energy efficient and lower fuel consumption. The downside is that the limit on the heat exchanger here is roughly 50, on the high end 70%. And when you run it through the system and through the calculations, you'll see that it actually ends up consuming quite a bit more than an RTO does. And I've got a slide coming up here in a little bit that'll actually compare all these technologies under the same process conditions. So you'll get a pretty good idea of the difference. A thermal recuperative unit. There's a very niche market for these type of systems. Again, this is a thermal oxidizer, so this does not have catalyst present, so it operates kind of like an RTO, but the heat exchanger, just like the catalytic unit, is much lower efficiency than the RTO, so it's again in the same 50 to 70% range. And because it is less efficient, it can handle higher VOC concentrations, so this unit can handle up to 50% LEL, where the catalytic unit and the RTO are limited to 25%. But again, very niche market. So where we would see these applied are where there's a silica dust type of application, like a silicone type coating line, where those silicone vapors, when oxidized, will actually create a solid silica dust. That can cause some problems within an RTO in terms of plugging up the ceramic media, and with catalyst as well, it'll plug the catalyst blocks. So that's where we would see these applied. Secondly, when I get to the concentrator system, you'll see that there's an oxidizer still tied to the concentrator system. It's pretty common to see a thermal recuperative unit in conjunction with a concentrator system, mainly because we are concentrating the airstream, so you tend to get into the higher percent LEL loadings. This slide, and then again on the next slide, which will be that vapor combustor. Again, these are the opposite of the RTO in terms of energy efficiency. So really where these tend to be applied are in chemical plants like a batch application with very high loadings, or an inert stream where it's either nitrogen blanketed or inerted with another compound. And again, there is no internal heat recovery, so if there is low VOC loadings, then you're looking at a very large gas bill at the end of the year. And on the next slide here, the same thing applies to the vapor combustor. Really, the applications for the two are very similar. The vapor combustor tends to be applied more to the oil and gas industry. They're much more common in there. Also, you'll see these applied very commonly to tank farms where we're treating just tank vents, or say barge loading or truck loading or rail car loading applications. This is the emission concentrator system that I had talked about. Now, one thing to keep in mind as I talk a little bit about this is the concentrator system itself is really two parts. There's a concentrator wheel where you can see that's in the cutaway on the left-hand side of the schematic there, but there's still an oxidizer present. So the concentrator wheel itself is really what it does is takes a very large air volume, very dilute stream, and concentrates it down to a smaller volume so that we can send it to a smaller oxidizer using a lot less fuel. Typical air volumes here, as low as maybe 10,000 CFM, but in reality, they're typically in the 50 to 60,000 CFM as on the low end, multiple 100,000 CFM on the high end. So really where you see these applied are, if you can imagine what it takes to paint an airplane, you can't put a close capture hood over an airplane, so you're basically evacuating a hangar. So you're looking at potentially hundreds of thousands of CFM with very, very little solvent in the airstream. That's where this would be applied. Also, the semiconductor industry, extremely common for a different reason there. Now, those airflows in the semiconductor industry can be very large as well, but they also tend to be very prone to pressure fluctuations, where the RTO inherently can have a very small pressure fluctuation where it can cause operating issues back at the actual process. For those applications, we would install this concentrator wheel between the RTO and the actual process. So just to give you a visual representation of what it does. So again, for easy math purposes, assume you have a process stream of 100,000 CFM and 10 pounds per hour of VOC. What the concentrator wheel will allow us to do is on the low end concentrate it down to by a factor of 10. On the high end, we can actually achieve around 20 to 1. So we can take 100,000 CFM and 10 pounds per hour, go through the concentrator wheel, and the result is we can have a concentrated stream of 10,000 CFM and still the same 10 pounds per hour. And that 10,000 CFM stream is then what will be sent to the oxidizer, as opposed to having to heat up 100,000 CFM. So again, what this all gets back to is operating cost of the system. Which leads us into the second poll question that we have. What is the most important factor driving your environmental purchasing decisions? Again, we'll take 15 seconds or so. Okay, so regulations by far the leader, operating cost in second there. Okay, always, it's good to know. So to wrap all of this up in terms of operating cost of the various technologies, what we took is a fictional application here of 10,000 CFM of process air, 100 degrees Fahrenheit, and 15 pounds per hour of styrene, and then applied some arbitrary utility cost to it of $5 per million BTU and 7 cents a kilowatt hour. And then calculated what the total operating cost would be, assuming that application for all of these technologies. And you can see the drastic difference from top to bottom, where The DFTO, you're looking at about $90 an hour ongoing for the entire time that thing is running versus the concentrator on the bottom. And a couple that I'd like to point out too, the difference between the catalytic unit and the RTO. Again, the catalytic unit has a lower operating temperature, significantly lower operating temperature than the RTO, but the difference in energy efficiency is really the driver there. So even though the RTO operates at 700 degrees hotter than the catalytic unit, it still is overall about half the operating cost. Now you can also look at that and say, well, the concentrator is clear-cut the winner. You should use it every time. The problem here is on an airflow of this size, the capital cost of the concentrator system would be prohibitive compared to the RTO. So even though it's over a third less operating cost than the RTO, the capital cost is probably 3 to 4 times as much on a system of this size. Once you get into the 40 to 50,000 CFM range, that's where the capital costs between the RTO and the concentrator are much more in line. These next 4 slides talk really more about how to, I guess, properly maintain the system once it's on site. So I'm going to skip through these fairly quickly here. And actually, we have one of the files that you can download is our Oxidizer Service Series, which this is a few of these bullet items are cut and pasted out of there. So really just wanted to make you aware that you do have the opportunity to download that and talk about or look at all of these in a little bit more detail. One of the key items here on item number 5, now this applies to new equipment and if you're looking to upgrade or retrofit existing equipment, is there are multiple programs out there, government-funded programs, where you can apply for rebates, and they will end up paying for large portions of the project. We've worked on a number of projects where that's applied. Bullet item number 9 here. This is one of the things that people tend to not think about either. Is we've seen it quite often actually where air permits. The permit itself has required the end user to perform annual maintenance. So not only does it help in terms of maintaining and useful life of the system and operating costs, in many cases it can also be a requirement in the permit itself. Secondary heat recovery. One thing to keep in mind is this always seems like a pretty good idea, and for some technologies it does really work well. For example, like the direct fired system, you have going out the exhaust stack, it can be 1,500 degree air going out the exhaust stack, so you can have a lot of energy there. Now on the RTO side, the RTO is designed to be internally energy efficient. So the majority of the heat is kept internal, so it's more applicable to the less efficient technologies. And this is the last slide I have here. This is one of the unique applications where we tend to have a halogenated airstream. So, for example, methylene chloride, methyl chloride, methyl bromide, those sort of compounds, or a stream that has sulfur-containing compounds such as hydrogen sulfide. The same oxidation reaction that we talked about before still applies to these applications, but in addition, now we're also going to create an inorganic acid. So methylene chloride, for example, when broken down, you're going to create hydrochloric acid. Now it creates a number of other concerns within any of these oxidizers, but what it'll also mean is in many cases, a secondary piece of equipment is going to be required to neutralize that acid. And that secondary piece of equipment is usually a wet scrubber. And with that, I'll hand it over to Brian.
Okay, so I'm Brian Kunkle with Verantis. I'm going to go through just a brief overview of some wet scrubbing considerations here today. We're going to talk about some types and classes of air pollutants, and also we're going to cover very briefly some basic wet scrubber types, but we're going to quickly focus in on one type that is by far the most commonly applied of the various options for a thermal oxidizer vent application. So covering the general briefly here, there's actually, some, at least by definition, a lot of crossover between some of the same types of issues that can be solved using wet scrubbers. In many cases, can also be solved via thermal oxidation. Everything has its place. So when it comes to wet scrubbing after a thermal oxidizer, we're generally only worried about a few of these, mainly the gases, the HAPs, okay? HAPs include certain VOCs. They also include the various inorganic acids that Scott mentioned that can be formed as a natural part of combustion of certain contaminants. Wet scrubbers are also used for various particulate applications, both for just reduction of particulate and also for specifically reduction of opacity or visible particulate coming out of an exhaust stack, as well as all sorts of odor applications. But as far as thermal oxidation goes, the real focus is inorganic acid production. So again, briefly on the general, wet scrubbers can be used to approach basically all sorts of gaseous pollutants, many of which are included on this list, aside from many of the VOCs, something like toluene, things that are insoluble, things that have high vapor pressures and are non-reactive as far as the scrubber is concerned. Those would be definitively thermal oxidation problems. As we move through a thermal oxidizer, we're going to end up with compounds like HF, HCl, HBr, SOx, which often manifest themselves primarily as SO2 as far as our wet scrubbers are concerned, and chlorine, bromine, and related compounds. So when we look at a wet scrubber design, there are really three core considerations to make when we look at a given pollutant that we want to control: solubility, volatility, and reactivity. These can be used sometimes alone and sometimes, in many cases, in combination to effectively wet scrub a compound. It's important that we emphasize that solubility alone is not enough to make a given pollutant viable for scrubbing with water. There are many compounds that you will find good, reasonable, high published solubility data for, but they have very, very high vapor pressures above such a solution as well. So I know, for example, sulfur dioxide, you can find some published data which tells you that it's got a solubility in water. You would not be able to economically scrub sulfur dioxide using water only in most cases because of its very high vapor pressure. So when you consider a pollutant for wet scrubbing, if it's soluble and has low volatility, then it's probably a good candidate for water scrubbing. If you can get the material into aqueous solution and it can be rapidly reacted with a reagent like sodium hydroxide, for instance, then it's likely also a good candidate for wet scrubbing. If the gas is fairly non-reactive with typical chemicals available for neutralization, or it's not reactive at a rapid enough rate, then you probably are looking at a different technology like a thermal oxidizer to control that compound. So a couple of examples, typical, again, of thermal oxidation. Of course, these are only a few reactions. There would be, dozens and dozens of specifics, but these are fairly representative categories. Your hydrochloric acid, hydrogen bromide, hydrogen fluoride are very common. Sulfur dioxide and chlorine as well. HCl and HF can, in many cases, be scrubbed to fairly high efficiency using only water, if preferred. Most of the time, folks are looking to neutralize them anyway, and so we'll go ahead and add a neutralizing chemical like we show here in the top reaction, combining HCl with sodium hydroxide to make sodium chloride, simply because they're only, it's coming in at fairly low concentration, and they're going to need to deal with that anyway before they discharge it to wastewater. The SO2 and chlorine scrubbing reactions, there are other chemistries that you can certainly use to approach these compounds, but without some kind of neutralizing chemistry, they can't be effectively scrubbed. So, you know, something has to be added to the system to make that happen. So we talk about a wet scrubber, and let's go through a real quick definition here of what exactly we're talking about. It's essentially just, it's a device that, any device that allows us to extract particulate, solids, liquids, gases from a gas stream and transfer it to the liquid phase, whether we simply dissolve it, we neutralize it, or it's just a solid that's captured there. So obviously what we've been talking about here with thermal oxidation emissions are contaminant acid gases. We're generally looking to absorb and neutralize those compounds into our solution. You are typically, again, there are many types of scrubbers. We're always looking to get the necessary efficiency for pollutant removal with the minimum capital and the minimum operating costs. That drives so many things, and that really drives us toward, you know, whatever type of technology we're looking at in terms of scrubbers. We're going to focus in on a PAC Tower scrubber here, which is almost always the correct answer to the most economical question for these applications. We look at the rationale of why use a wet scrubber instead of some other type of technology or a dry scrubbing technology as an alternative. A wet scrubber is going to typically be an excellent fit for inorganic acids, which is why we're talking about wet scrubbers here today with respect to thermal oxidation and its off gas. But just in general, if you're dealing with soluble gases, gases that are reactive with water or with an aqueous solution, a wet scrubber is generally going to be very effective. If the pollutant is simply cannot be effectively removed or not effectively enough in an alternative dry form, you know, this comes up from time to time. Sometimes these scrubber efficiencies are required, you know, 99.9% and beyond. Sometimes a wet system is able to drive to a little bit higher efficiency. If you already have liquids or condensation present in the gas stream, whether that's your contaminant or not, a wet system is typically going to be, you know, very well able to manage that from a material handling standpoint and uptime. If you're looking to, if you must neutralize anyway, or if you're looking to do some product recovery, for instance, you want to collect HCl and make HCl solution that can be fed somewhere else in the plant to be used. Perhaps you have, you know, a contaminant that you can make a useful salt or something that will simply make it less expensive to dispose of. And these are all considerations that can be incorporated a lot of times into a wet scrubber design. And, you know, in some cases you'll have pollutants, not necessarily off of a thermal oxidation process, but you'll sometimes have pollutants that are just a little bit more safely handled wet than dry. So wet scrubbing is obviously a very simple concept, but we wanted to emphasize there's two steps in this process. The step that we all focus on is the capture of the contaminant of interest in the first place, in a packed bed or a venturi throat or wherever it may be. But it's important to note as well that once you've done the scrubbing and that gas stream exits the scrubbing device itself, it's very important to have a good, well-designed gas discharge section, including the entrainment separator, to make sure that you don't re-entrain droplets that contain your contaminant or byproducts thereof and send it right out the stack after you've already cleaned the gas. So the gas stream has to flow by some kind of liquid distribution device, and that's typically what we're concerned with here. So the design and consideration of the scrubbing portion as well as the mist separation portion are both very important. So the basic types, in addition to, we didn't list here anything in depth with electrostatic technologies, which also exist, or hybrid technologies, but spray towers, countercurrent PAC towers, packed beds in a crossflow configuration, tray towers, and venturis are fairly ubiquitous. They are widely applied. But what we're going to talk about in a moment here is really just the countercurrent PAC tower. It's got excellent gas removal capabilities, compact footprint, and fits very well with the types of off-gas that come from a thermal oxidation system. So this is a basic diagram of a PAC tower. I should note as well that if you guys have any questions that should arise about other types of scrubbers, please submit them to us. We'll answer those just like all the others. The PAC tower is very simple, no moving parts. Dirty gas flows in the bottom. We clean it in the packed bed. We flow through the packed bed from bottom to top. The gas flows through the system, and the liquid contacts the gas in the packed bed by trickling down through. So here you'll see a little bit more detail. We have a liquid sump, which is typically used for recirculation purposes when we're scrubbing inorganic acids, like we would be in a thermal oxidation vent application, and then basic gas inlet, packed bed, and on through the system. We'll talk briefly here about considerations for the packed bed itself. The packed bed is where the action happens in terms of the scrubbing process. We could do a whole webinar on just packing, and we obviously don't have time for that. So I'll just briefly mention that there's two major classes of random scrubber packing. There's extended surface and there's filamentous types. Extended surface would be saddles and rings, that type of thing. I've got a picture of some filamentous type packing here on the slide. The filamentous packing is typically preferred for these applications because it relies on a very small actual area of packing facing the gas stream, and it uses those shapes of the packing to break up the liquid so that you get very, very high liquid to gas contact area. What that means is, comparatively speaking, you end up with very effective mass transfer at low energy cost and low pressure drop. So you end up with smaller scrubbers that can run at 500 to 600 foot per minute gas velocities, high efficiencies up to and exceeding 99.99%, depending on what's needed and what the compound is, and pressure drops across the packed bed, let's say in the 1 to 4 inch water column range. So that's typically what we would look at is such a packing. Quite commonly for these applications, the performance requirements range from 95 to about 99.9% most of the time. As we travel up with the gas stream, we look real quick at the liquid distribution system. Typical liquid rates through these PAC columns would be about 10 to 12 gallons per minute per 1,000 CFM of gas flow. The key consideration here is that you really want your liquid to be very evenly distributed across the top of the packed bed, because this type of packing is not going to self-correct any maldistribution. What comes in the top is largely going to go through. So a lot of times you'll see an arrangement like we have pictured here with a full cone, full coverage spray pattern out of a spray nozzle, just to make sure that we get really very even coverage across the top. When you have coverage problems, you have issues with liquid distribution throughout the bed, you can end up with performance issues. So the entrainment separator that we mentioned earlier is then downstream of everything else in the tower, and the gas stream is going to flow through here, and any liquid droplets that it picks up from the liquid distributor itself will be separated here. So most commonly we're talking here about mesh pads or chevron blade assemblies. And typically these would have about a 1/10 of an inch to maybe 1 inch of water column pressure drop across them during normal operation. So I'll summarize briefly. The countercurrent PAC scrubber is a vertical configuration. Gas flows up, liquid flows down, hence the countercurrent label. This type of scrubber is very good for removal of gaseous contaminants, which is what we have to deal with in these applications. This type of scrubber also happens to be very effective at removing particulate, liquid droplets and solids that are above about 10 microns in diameter. You wouldn't necessarily prefer to use it for that if those things are insoluble. Soluble would be much better, so you don't have to worry about fouling. But nonetheless, this type of scrubber is very effective for that purpose. And finishing off the summary of the PAC column, just a couple more, I guess, design points and ranges to think about. We can typically operate these really approaching 600 feet per minute. Again, there are some variations depending on the efficiency requirements and the compound that we're trying to attack. The packing selection is important. It's important to work with something that's going to give you, the best energy costs as well as size of the equipment. The total flange-to-flange pressure drop across a PAC bed is typically going to range from maybe 1 to 6 inches of water column, probably averaging around 3 to 4. Okay. One special note for the scrubber downstream of a thermal oxidizer. No matter what the type of thermal oxidizer is, the gas is typically going to come off at a fairly high temperature in comparison to the scrubbing equipment itself and what it can withstand. So we have to integrate a pre-cooling stage. Typically we're looking at a direct contact adiabatic quenching system where we're just contacting a relatively large amount of water with the gas stream itself to drop the temperature rapidly. It's an important note that sometimes we might think that we have to try to drive the gas all the way to its saturation temperature, but that's not really the case. You just need to drop it to what's safe for the downstream equipment, which would normally be somewhere in the 180 to 220 degrees F range. Here's a couple of examples of quench arrangements. On the left, we have a lower temperature design. The horizontal design is not quite as ideal for gas and liquid mixing as the vertical design, and it can extend fairly long if the temperature gets higher and higher. That's when we transition to a vertical design, which allows us to conserve space in the footprint and get a little bit better mixing and more easily vary the residence time. A key with the quench design is we have to look at what's the inlet temperature, what's our safe outlet temperature, and then we have to make sure we have excellent mixing and we have adequate residence time. Another key consideration with a quench is we want to make sure that if we are recirculating anything to the quench and we recirculate any salt solution, we don't expose that to the very highest temperatures in that quench because we can over-evaporate and actually take that salt solution and make it into a submicron particulate that can come out your stack. About the last one here. So just a quick visual for you guys. We have an adiabatic quench from an actual system. I believe the inlet temperature was about 1800 F here. The gas flows down on the right-hand side through the quench, up through the PAC Tower, and out through an induced draft fan. As Scott said, most of these systems will have the fan at the tail end of the system such that any leakage comes into this system rather than out with these hazardous compounds contained therein. And the last couple slides here are really just sort of a reference for after the fact for you, so you can do a little cross comparison of the different types of scrubbers since we couldn't really talk about them here today in full. I'll give it back to Mary.
Thanks, Brian. As you can imagine, we tried really hard to cram as much information as we could into an hour here, but these are two topics that quite frankly could be an hour and a half on their own. So hopefully it gives you a nice overview. Before we move on to our Q&A here, though, just want to talk a little bit again to remind people who are here for the credits portion. Don't forget, you do need to take the quiz, which is the green widget on the bottom, and when you are done with that, move on over to the yellow widget where you can print your certificate. If we do not get to your Q&A question here, don't worry about it. We definitely will get back to you afterward. Either we'll email you directly, call you, one way or another. After the audio portion of this presentation basically ends, the platform itself is actually still going to be available for another 30 minutes, so that will give you a chance to go and take the quiz or go on over and take a look at the resources that we've provided, print them out, ask some more questions. We'll actually still be here to answer questions for that 30-minute period, so feel free to stay on and ask a couple more questions and we can get back to you. But we have a couple minutes here just to answer a few questions, but thank you for definitely coming to us today. And Michelle, I'm going to pass it on to you for the Q&A portion.
Absolutely. Thank you, Mary, so much. Thank you both, too, for the information today. We do have a ton of questions, and just as Mary said, if we don't get to all of them today, we will be following up with you after the event, so we can go ahead and get started. All right, guys, first question. When would someone go with a catalytic instead of an RTO?
Okay, I'll take this one again. This is Scott Bayon with Anguil. When would you go with a catalytic over an RTO? One on the lower airflow volumes I'd mentioned. So I would say, again, in below 5,000 CFM, really around 3,000 CFM below for sure, you would look at a catalytic unit. The main reason there is the RTO will still use less fuel and will have a lower overall operating cost, but the savings is so low that it won't offset the capital cost. The catalytic unit will be less expensive in those flow ranges. Also, where footprint or weight are a concern, we see a number of our customers looking to install these units either on a mezzanine or on a roof of a building, or limited space in a yard or a parking lot, that sort of thing. A catalytic unit of the same air volume capacity compared to an RTO will have a significantly smaller footprint and be a fraction of the weight. Again, the RTO is full of the ceramic block, which adds literally tons of weight to the system. So in reality, that's where we tend to see the catalytic units applied: smaller airflow volumes, or where weight and or footprint are constraint concerns.
Great. Thanks so much for that answer. Next question is in regard to spray nozzles. Do you notice that they have any problems, or can they become high maintenance?
Generally, they should be low maintenance. We would recommend that we would recommend whatever the arrangement is. We try to go single nozzle wherever possible, or as few nozzles as possible for a given spraying application. That means that your orifice size in that nozzle is going to be as large as it can be. So from the standpoint of anything relatively large coming through and blocking the nozzle, it should help to avoid those problems as much as you can. We would always recommend that a strainer be placed upstream, so that, again, you try to mitigate any major issues. You'd rather catch those somewhere easy to maintain than in the nozzle itself. From the standpoint of, I'll say, just general sort of deposition and fouling, that type of thing, as long as the system isn't being operated, too close to or an exceedance of solubility limits for, any salts, for instance, that are building up in the system, we wouldn't expect to see any major issues with that over the course of time.
Perfect. Thank you so much. All right, it does look like we have time for just one more question before we finish up with the presentation today. I'll just get right into it. What is the inlet temperature limit for a scrubber?
We didn't get in much to the materials and construction on the scrubber here, or really at all today, but most of these scrubbers are, I guess, most economically applied if they're built out of a material like fiberglass. Gives you a lot of corrosion-resistant properties and is, a pretty robust material mechanically. We can design a fiberglass scrubber tower and internals for, continuous operating temperatures up to, let's say, 300 degrees F, but that would be fairly unusual and generally actually not required for this kind of application. Most of the time, the gas temperature, even from a from an RTO or something along those lines, will pretty well exceed what we'd want to look at for operation of the downstream scrubber. So we're going to work in a quench, even if it's a relatively small, limited requirement quench. And so, to make a long story short, typically, safe operating temperature for the inlet would be something below around 220 degrees F. And normally you'd have really no issue continuously maintaining less than 200 degrees F, giving you a little bit of a buffer. By staying in that temperature range, you don't have to worry too much about overly exotic formulations of the fiberglass or any other more exotic materials for the scrubber. And your saturation temperatures that are ultimately going to be cooled to once you get into the scrubber are typically going to range somewhere around 180 F or below anyway. So if you can get into the scrubber at around 200 or maybe a little bit above that, you're going to rapidly cool down and you'll be fine.
Great answer. Thank you so much. It does look like that is all the time we have for questions today. We do want to thank everyone for joining us today, taking the time to attend this webinar, and thank you so much, Scott, Brian, and Mary, for also taking the time today and presenting that information to us. Just a quick reminder, if you haven't yet, please take a few minutes to complete the exit survey on the console. In an effort to make each of our webcasts beneficial to you, we would appreciate your input. You will also be receiving an email following this webcast that will contain a link to the recording of today's program. The email will be coming from the EHS Daily Advisors. Just keep an eye out for that in the next few days. And again, thank you so much for joining us. EHS Daily Advisor, Verantis, and Anguil would like to thank you again. This concludes our program.